Have you ever just watched a river flow? It seems so smooth, so seamless, right? Or how the air around you feels like one continuous thing. Well, that's how we see fluids. But here's the crazy part. It's all a grand illusion. The reality is, any fluid you can think of is made up of countless separate molecules, all just chaotically bouncing around. So, which picture is the right one? Let's figure it out.
You know, this analogy is just perfect. It totally nails the two ways of looking at a fluid. From way back here, our perspective, it's a smooth, continuous painting. But if you could zoom way, way in, you'd find a world built from individual little dots, the molecules themselves. So this is the big question we're going to tackle. And trust me, it's not just some academic puzzle. The answer to this determines how we model everything, from the weather outside to a spacecraft burning through the atmosphere. It's all about knowing which set of physical rules you need to play by.
So, to get to the bottom of this, we're going to start with that grand illusion of smoothness. And then we'll dive right into the microscopic chaos of the molecules. After that, we'll introduce our referee of scale, see how it makes the call, and finally, check out some mind-blowing real-world examples.
Okay, let's really get into this. The whole idea that fluids are continuous just feels right, doesn't it? I mean, we talk about the pressure or velocity at a specific point in the water, as if you could just keep dividing it forever. But deep down, we know that can't be true. It's an incredibly useful illusion, but an illusion nonetheless.
I mean, look at the difference here. It's pretty stark. On one side, you've got our everyday experience, a nice, smooth, flowing river. On the other side, you've got this frantic, hidden reality that makes it all possible. And that's where physics comes in, giving us the tools to connect the two and see how one emerges from the other.
All right, now it's time to zoom in. We're going right past the smooth surface of that painting to see the individual dots. So I want you to imagine a tiny bit of air, but don't think of it as calm and empty. Oh no. Picture a three-dimensional pinball machine, absolutely packed with trillions of tiny, tiny billiard balls. Yeah, this world is anything but calm. These little molecular billiard balls are zipping around at unbelievable speeds, constantly smashing into each other. And what we feel as temperature, that's literally just the average energy of this chaotic dance. The hotter it gets, the crazier the dance becomes.
Now, in all this chaos, there's one measurement that is absolutely crucial. It's called the mean free path. Basically, it's the average distance one of these molecules gets to travel before it smacks into a buddy. Think of it as the average amount of personal space in a wild molecular mosh pit. For the air around us, it's super, super small, like 68 nanometers. But the fact that it isn't zero, well, that's the key to everything.
And this is how we get things like pressure. It's a kind of statistical miracle. That steady force you feel from the air isn't some continuous push. No way. It's the combined, averaged out effect of trillions upon trillions of individual molecules hitting a surface every single second. It's a smooth force born from pure, discrete chaos.
Okay, so we've got these two different worlds, right? The smooth, big picture world we can see, and the chaotic, tiny world of molecules. So how do we connect them? How do we decide which description is the right one to use? Well, for that, we need a referee.
And the whole decision really just boils down to a simple comparison of scales. That's it. On one hand, you have the scale of the molecules themselves, which we can define by their mean free path. And on the other hand, you've got the scale of the system you're actually looking at, say the width of a pipe or the wing of an airplane.
And the solution is this really elegant little thing called the Knudsen number, or Kn for short. It's this beautiful, dimensionless number that acts as our referee. All it does is ask a simple question. How big is the molecule's personal space compared to the size of the whole playground? And the answer to that one question changes absolutely everything.
So, we've got our referee, the Knudsen number. Now let's see what its verdict actually tells us. Because depending on whether that number is big or small, the fluid has to play by a completely different rulebook.
This table just lays it all out perfectly. Check it out. When the Knudsen number is really small, we're talking less than 0.01. It means the molecules are constantly bumping into each other. They're always talking, sharing energy, and averaging out their behavior to act like one smooth thing. That's the world of rivers and weather patterns. But when the Knudsen number is huge, the molecules hardly ever hit each other. Their entire existence is dominated by hitting the walls of whatever they're in. That's the reality for something in the vacuum of outer space. But of course, it's not just a simple on or off switch. There's this super tricky transition zone right in the middle, where the physics is this messy combination of both worlds. And trying to model that middle ground, that's one of the biggest headaches in all of fluid dynamics.
And I want to be clear, this is not just some abstract theory for a textbook.
Understanding which regime you're operating in is absolutely critical for designing some of our most amazing technologies. The Knudsen number isn't just a number, it's a vital guide for engineers and scientists.
Okay, so let's take a spacecraft in orbit. Way up there, the air is incredibly thin. That mean free path, the molecular personal space, is massive. It can be meters long. So compared to the size of the spacecraft, the Knudsen number is super high. You simply can't treat the air as a smooth fluid. You have to switch to a free molecular flow model and actually track individual particle collisions. Now let's contrast that with the very same spacecraft but during re-entry. As it plummets back to Earth, the atmosphere gets denser and denser, and that mean free path shrinks like crazy. Suddenly, the Knudsen's number gets really, really small. And just like that, the air starts behaving like a classic fluid, and the continuum model works perfectly. The physics completely flips during that one single trip. And this concept is everywhere. It applies at the tiniest scales, like in microfluidic chips, where the channels are so small that even air at normal pressure can act weird. It's crucial for understanding how bacteria swim, for designing new materials. Really, it's a fundamental principle of scale that shows up all over the place. You know, this whole journey from a smooth river all the way down to the chaotic dance of molecules, it leaves us with a really fascinating thought to end on. We've seen how a continuous reality can emerge from something that's totally discrete. So it makes you wonder, what else in our lives, from maybe the flow of time to our own consciousness, seems perfectly smooth on the surface, but might actually be built on hidden, granular foundations? Yeah, that's definitely something to think about.